Well, thank you for the introduction, Tanya. So I would also like just to mention our external collaborator, Feng Shi at the University of Delaware, who's been um, in charge of all of this development on the Funwave model. So to start with, I'll just give a brief overview of today's tech discussion. I'll give a brief overview of the Funwave module, then briefly discuss the Tidal Surge module, and then to update you on the ongoing work on the deep water module. So Funwave is a phase resolving numerical wave model, for shallow to intermediate water depths and resolves many physical wave processes. So looking for an example, if we look to the left of the structure here, we see these reflected or refracted waves traveling away from it. Similarly, if we look to the top of the structure here, we see as the waves pass, they bend and diffract and bend inwards. So I should note that these underlying terms here are phenomena not natively available in phase average models. So continuing on with the simulation, these waves generate waves generated by the wave maker results in these induced currents, and as these waves propagate, transform and are transformed by the bottom friction, nonlinear wave interactions, and current interactions. This results in the nonlinear shoaling. So as you see, as these waves shoal, they begin to break up, run up, and you eventually have some overtopping. So if you look in this region right here, you see that these puddles have filled in, creating some overtopping. So it's kind of hard to see the run up and overtopping, but this top illustration kind of shows it. So you have the wave generation, the shoaling and overtopping, the run up, the eventual overtopping, and then the flooding on the backside of the structure. So I also like to note that Funwave has several military applications. So these are marked in blue. So in this video, I showed the flooding example of flooding threats. So if we kind of focuses in this harbor region, you can kind of see this very complex dynamics. And it's just basically a combination of all these effects I discussed in the first 3 points. So in particular, this understanding these wave conditions is important for successful littoral entry options, in particular where there's very little military presence. Moving on to the fourth point, Funwave has been used to model harbor resonance and infragravity waves. So continuing on with the idea of military applications, and difficult to access ports of entry, understanding these additional complications to the local wave conditions is critical for maintaining reliable and efficient logistics over the shore. Personally, for the 7th point here, Funwave, I personally use the Funwave vessel module and sediment transport module and morphology change in various projects. Funwave has also been used to model landslide generations and landslide generated tsunamis. So I kind of mainly discussed the improvements to the Funwave model and extensions to the physics of it, but we've also made several efforts in improving the Funwave usability and user friendliness. So one of these efforts is the HPC portal, a web-based GUI with access to DoD HPCs. It's also note Funwave is open source code. The code is available in a version controlled GitHub repository. There's a wiki link here with the Funwave manual and the supporting materials. And to start to segue into the next slide, Funwave can be thought as sort of a bridge model or gap between higher fidelity 3D models and phase average models. So in some sense, it can be thought as balancing computational costs with the accuracy of the underlying physics. So give some motivation on this idea of bridging the gap as one reason why boostiness type models have become very popular in the past 2 decades. This is mainly to 2 advantages. Firstly, Funwave is a depth average approach that removes the Z dependence. So we're going from XYZ to XY. So this reduces the computational complexity. Secondly, Funwave is second order Boost-Ness type equation, which is weakly dispersive but fully nonlinear. What this means is that physically these waves feel the bottom, and thus move at slightly different speeds. So the waves spread out, disperse, hence weakly dispersive. So conversely, if you think about the shallow water limits, all the waves travel at the same velocity, but at different depths. In the deep water, they all travel different. Sorry, in the deep water, all waves travel all different velocity, but are independent of the depth. But as you go into shallow water, all the waves have the same velocity and only vary depth. So in other words, these wave velocities travel from, depending on the wavelength in the deep water, to a common single velocity in the shallow water. So the point out of this was I just kind of want to highlight the complex wave-wave current interactions and the transition regions where waves start to feel the bottom and don't feel the bottom. The increased popularity of these Boost-Ness type models means Funwave has been applied to more complex simulated scenarios. So in one direction, we've been applying Funwave to larger and larger domains, and pushing it into deeper waters. So an example here, we kind of have a simulation of two vessels passing by each other. In another direction, Funwave has also been carried out for a longer time. So we've necessitated the need to include tides. Also, including tides is particularly important for low-lying areas because small changes in the water levels can mean the difference between flooding and no flooding. So connecting back to what I mentioned, the two Funwave modules in the beginning, there's a tidal module for the longer times and the deep water module for sort of going into deeper domains. So before I go to discuss the tidal forcing module, I just want to note that here I'll be using H and L, H over L interchangeable KH. KH is the wave number, which is 2 pi divided by the wavelength. So the idea of the tidal behind the tidal module in Funwave is to use tidal or surge data as boundary condition inputs in Funwave. So currently in Funwave, there's two different methods. The first method is absorbing tidal boundary condition, which can be thought of as being analogous to the sponge layer implementation in Funwave. So in the sponge layer, we're dampening the water levels and velocities to zero. However, now with this tide module, it's very similar methodology, but now we're just specifying non-zero or time-varying values. So I'm kind of using dampening and absorbing interchangeably. So in the case of a sponge layer, it's absorbing or dampening the waves before they reach the boundary, whereas the tidal BC is kind of absorbing any incoming waves, such as to satisfy the boundary conditions. This boundary could be applied at one or more boundaries. And as mentioned before, there's several types of input. I also note that I kind of use the word tidal a lot, but this time variant input will also storm surge data. So we can also, model storm surge input. So as you see this graphics playing here, we have a 2D plot of a Funwave simulations with tides and a wave maker, a 2D transect, and it kind of shown a snapshot here with a tidal level. As you go to the right, there's decreasing tide, or conversely, at this left boundary, there's an increasing tide. I'll also note that this wave maker is implemented separately from the tide module, and that you either have a sponge layer or an absorbing tidal boundary condition at each boundary. So they can be different, but it's either or. The second method is the absorbing generating tidal BC boundary condition. This could kind of be thought of as an extension of the first method, which basically combines the absorbing boundary condition with the wave maker. This is limited to the west boundary, and the main purpose here is to kind of simplify the coupling between the wave maker and the tidal forcing. So similar here, you have 2D plot of the wave direction, I think it's about 30 degrees. And this left figure kind of shows increase in tidal level from some earlier point to some later point. I'll note that this method is also a new type of wave maker, so it's kind of and it's currently limited to John swap or TMA spectra or some spectral data input or FFT input. So having given a sort of a brief overview of these two methods, are there any questions before I move on? Oh, sorry, west boundary offshore. Sorry, Hans, I missed that question. Yeah, so west boundary is typically, I guess, well, local to the grid. So we're thinking of going into negative X direction.
Thanks for answering the question, Michael. So is that the negative X direction? I forget how Funwave works. Is that implied the offshore boundary?
Yeah, typically it's the offshore boundary. So there's some technicalities there, but yeah, it's the offshore boundary.
Okay. All right. As long as the convention is square, right? Because on the West Coast, we're kind of like offshore is negative X, and on the East Coast, offshore is positive X.
Yeah. So
yeah.
Yeah, I know, and I know agree. It's also thing with Funwave being a rectilinear grid, so we even have to transform or rotate grids to get them to get the shoreline in the right direction and the local grid. So what's west, what's north, and the orienting directions kind of becomes arbitrary. Well, yeah.
Thank you.
No worries. Okay, then. So for moving on to some real world examples, here we have a real world example of Hurricane Irene at Norfolk with some tidal forcing. So here in this top figure, we can see the waves coming from the north downwards, impacting the shoreline. This top right figure here is a transect. One thing to note here is this red dot, which is the instantaneous sort of run up. And then plotting that as a function of time in this bottom graph. We have the run up as a function of time with these red circles kind of correspond to the max run up. And this is some joint work with Jack Paleo and Feng Shi at the University of Delaware. And sort of a storage first example, we have a 100-year storm event at South Bethany Beach. This storm boundary condition was taken from an older technical report. And here you just kind of see, the waves coming from the right, impacting the shoreline. You have overtopping, run up, and inundation, flooding, and flooding. So I can kind of give an example, an overview of the tide module with some, field examples. There's a technical note that's in the review that's finished the review stage is currently with the editor, so that should still be published, and so that should be still published. So unless there's any other questions, I'll move on to a bit of the discussion of the deep water module extension. So as I mentioned before, Funwave is limited to satisfying the KH less than pi limit, or alternatively, this is H over L is less than a half. While we kind of call this the deep water module, increasing this KH barrier, will actually technically allow deeper waters. So for a fixed K, we can have larger H, or shorter waves. So for a fixed H, smaller L or larger K. As I mentioned, while we can relax the KH limit by extending Funwave to include fourth order terms, it's however known that these fourth order Boson-X type models are highly unstable. So alternatively, alternate approach we've tried is based on surface flow techniques, which are commonly used for non-hydrostatic waves. So while the main application of Funwave is typically coastal waves and inundation, there's also some consideration for vessel-generated waves. So before I kind of talk about the surface flow approach more, I'll briefly make an aside on some of the motivations for relaxing this KH barrier from a perspective of vessel generated wakes. So kind of here in this left figure, we have an example of vessel traveling from the bottom to the top. Here, these dots kind of represent example gauges. With this middle figure example of the wave signals. Vessel wakes are typically episodic events. Therefore, computing spectra is not appropriate. So typically, a spectrogram, a sliding window FFT or time varying spectra is computed, which is in the top. And one thing I should note is that you can also apply time and frequency filters and compute the inverse spectrograms, so you can get components. So that's technically what's here. So going from the top, this middle finger is actually the ship wake signal, this blue curve. So that's pretty much the spectrum energy concentrated in this purple region. Next, you have the harmonics, which is this orange curve. And that's the spectrogram energy concentrated in this top portion with the orange, bluish green colors. And then finally, you have the infragravity portion, which is this purple line, which is this bottom portion of the spectrogram. While it's often useful to characterize vessels, it's often useful to characterize vessels using the Freud number. However, there's some choice in the length scale. So example Freud number is here, where U is the vessel, G is gravity, and H is the depth of the channel. Alternatively, we can also use the length of the vessel. What this means is, on the right, we have a spectrogram from a collection of Funwave simulations. The important things to note is going down, we have an increasing Freud number with respect to depth, and going to the right, we have increasing Freud number with respect to the length. Furthermore, the important thing to note is these horizontal dashed magenta lines, which represents KH equals pi. So the main idea here is, if we look at the top portion of these graphs, the main spectral energy is above this curve, which basically means that these ship wakes are outside the validity regime of Funwave. Whereas if you go to the bottom, this energy is below the curve. So this regime is where Funwave is valid and typically applies to larger vessels, as larger vessels are typically confined to deeper channels. So kind of summarize the point of this slide. The Funwave can generate waves outside the regime where it's valid. Therefore, relaxing this KH limitation will allow Funwave to model a wider class of vessel-generated wakes. Specifically, these generated ship wakes are correctly propagated and dispersed. So kind of clean up with the surface flow approach. This is still in development. I wasn't involved in the early development, so I'm still learning myself, and I'll give my best understanding. So the surface approach results in a sort of a new hydrostatic phase that adds a correction term into the velocity field in Funwave via a new dynamic pressure term. To compute this pressure term requires solving the Poisson's equation. One thing is that the Poisson equations is kind of computationally expensive. Therefore, we kind of use a partial implicit scheme to improve computational efficiency. Some preliminary results we have show pretty much good agreement between numerical solutions and analytical solutions with respect to the dispersion relationship. So here in this figure, we have the root mean square error between analytical results and numerical results for a wave where KH was 3 pi, 2 pi, and pi. So the main idea is we can see most of these errors are bounded by below 5%, the relative errors, And here, while I don't want to go too much into this, this bottom actually has to do with vertical layers. So I would note that these layers are not in the underlying Funwave model or in the correction step. So Funwave is still being solved in one layer, but these are rather in the Poisson equation we use to compute the dynamic pressure. So kind of give a summary of everything so far. There's several publications in progress, almost finished. We have a technical note on the Tidal module, which is with the editor. There's a technical report we contributed on the Funwave test bed that's also with the editor. We have a Journal of Ocean Engineers article that's past the peer review stages and just needs some minor changes. You can find the titles there. And then we're also the technical note on this deep water module, which is still work in progress. Going forward with the deep water module, we want to test it for more test cases. So I showed you the slides about motivations from Schickwake's perspective, and then we're also cases test this with wind waves. I also note that there's some cross collaboration with the engineering of nature, where we're using this forcing module with a couple of the sediment module to compare with some field data.